A typical attentive human has a response time of around like 1.5 seconds. The autonomy system, with its multimodal 360 sensing, is able to detect and respond to the environment in about 5 to 10x faster.
Hello, listeners. We have a special guest today to discuss Rivian's custom silicon chip announced at Autonomy and AI Day back in December. Welcome, Mukund Chavan, VP of ASIC Design at Rivian. Thanks for coming on to chat with me.
Thanks for having me, Austin. Glad to be here to talk about our first generation Rivian autonomy processor, which we call RAP1, and how we work together closely with our autonomy team on our large driving model, or LDM.
Awesome. Okay, this is great. People are going to love this. So let's dig into the technology details. And of course, eventually, we're going to want to get into why Rivian chose custom silicon. But first, I thought it would be fun to work up our understanding of the requirements of your autonomy workload. So, I know multimodal inference at the edge is a different beast than I think most listeners are used to thinking about. A lot of the conversations around, AI in the cloud. And so I thought it'd be fun if you can kind of educate us on what that means to do inference at the edge. So maybe starting like at the super highest level, and we'll work our way into the deep end. So like in the most simple reductive terms, what does Rivian's autonomous vehicle have to do?
Yeah, in the most simple reductive terms, an autonomous vehicle has to be able to sense the world around it, know its place in the world, know where it needs to go, and make navigation decisions along the way to reach to its final destination. To be able to do this, it uses a variety of sensors. So if I were to use the human analogy, it uses like camera, like sensors to see, which are like camera, radar, and LiDAR. It also then uses the GPS and maps information to know where in the world it is, and then another sensor called inertial motion unit, or IMU, to know its state at that point. And then it uses vehicle actuation using steering, braking, acceleration, etc., and navigate its way to its final destination. To be able to do this, we have the perception stack that runs in like a 100 millisecond loop. Although our sensors run faster than that at up to 30 frames per second, we have our localization and vehicle controls that run at 100 hertz to ensure like smooth actuation. And we have other sensors like GPS and IMU that run in the kilohertz range.
Oh, okay, awesome. That's really helpful. So let's dig into sensing. So there's sensing, and there's sort of knowing where you are in the world and acting. Sensing, you mentioned cameras, radars, and LiDAR. So that is a lot of incoming data and different types of data. So talk to me, like, how much data is this? What are we dealing with?
Yeah. So the Rivian R2 will have the one of the most advanced sensor suite of consumer vehicle in North America. We have cameras that are streaming in at an aggregate of 65 megapixels per frame. We also have high resolution imaging radar, as well as long range LiDAR that give high density point clouds. All of this goes into our autonomy computer that is powered by two RAP1 processors that is capable of processing 5 billion pixels per second.
Wow. Okay. Interesting. So you've got two RAP1s and you've got a perception stack, and the perception stack just has like a ton of data flowing from the perception stack into the RAP1 kind of constantly. So then now, as all of this data comes in, talk to me about what happens. I mean, there must be some sort of sensor fusion where you're taking these different modalities and understanding the world as an aggregate of that sensor information.
Yeah. So what we have is on the RAP1 chip, we have a state-of-the-art image signal processor that takes the camera, raw camera streams coming in from the 11 cameras, and it does pixel processing. And then what that means is we do things like the ISP does things like format conversion. It does things like region of interest cropping. It also does things like lens correction. So that's the function of the ISP. Then we also have compute capability to be able to handle the high density point clouds coming from our radar and our LiDAR. So all of this then feeds into, so we have all these sensors. We have to be able to synchronize across them. So we have frame synchronization that allows us to synchronize the frames across these different modalities. Then our autonomy stack has early sensor fusion and end-to-end model training, where we take all the sensor inputs, and that's our large driving model. This end-to-end stack takes the multimodal 360 sensing and takes that as an input and generates a world model, and it understands its own state in it, and also does trajectory planning so it can get to its destination. This whole model is deployed on our RAP1 processor.
Awesome. So you have all this incoming data from your perception stack, and it sounds like you sort of pre-process it or clean it up with the ISP. That takes care of the cameras. And then did you say, is there like pre-processing or kind of cleanup of the other like LiDAR or radar data?
So there's not, so they provide point clouds, so we can just take them, directly into the large driving model. There might be some pre-processing that we do, but not a whole lot, because we get the object list and point clouds from the radar and the LiDAR.
Okay, got it. And so then you've got the cleaned up camera data and the LiDAR and the radar, and then you're syncing those to make sure that it's like representing what they're all seeing at the exact same time. That makes a ton of sense. And then it feeds into the large driving model. So let's dig into the chip. So obviously the RAP1, it's got the large driving model on it. It's got a ton of data that's coming in, kind of getting pre-processed, tightened up to be in lockstep. Talk to me about, actually, let's talk about the real time and sort of safety constraints as we're working through this workload. And as we're talking requirements, I mean, we've already hit on that we have to be able to handle a lot of data and we have to be able to do it quickly. You talked about doing this at 100 milliseconds and then even faster for the actual sensors. But this is obviously like a car that's driving itself. And so it's super important. If it sees something and you need to change the trajectory, you obviously want to do that as fast as possible or apply brakes as soon as possible. But I think a lot of us aren't that exposed to like real-time safety constraints every day. So could you sort of teach us at a high level, like what that means for the chip?
Yeah. So there are a couple of things that I'll decompose that question into. The first one is just, what's the response time, right? A typical attentive human has a response time of around like 1.5 seconds. The autonomy system with its multimodal 360 sensing is able to detect and respond to the environment in about 5 to 10x faster. And the second part is, determinism. So determinism is a key attribute of physical AI and robotics. And the system needs to be deterministic. So running a sophisticated model such as an LDM on chip, we have to required to carefully balance the workloads across the various hardware resources like sensor processing, neural network, memory, as well as CPU and GPU compute. So then our in-house firmware stack, which includes like drivers, middleware, as well as schedulers, it ensures that every step of this processing chain is optimized to run in real time with performance and determinism guarantees. So the processing chain is broken up into tasks, and then we use techniques like data flow graphs, etc., to map those tasks onto our hardware resources so that the hardware resources are maximally utilized and we can get a minimum latency. And then you talked about safety. So safety is a critical part of our overall thinking, and it's very important to us. We built our entire vehicle from sensors to actuators with functional safety ingrained in the architecture. So starting from RAP1, the RAP1 itself is manufactured in TSMC N5A, which is an automotive process, and it has a dedicated ASIL D safety island, which is the highest automotive safety integrity level. We also have our application cores that are ASIL rated, and our neural network engine is also designed with ASIL rating in mind. And then going from that, we have our autonomy computer that has two of these RAP1 chips for redundancy. And then to each of these RAP1 chips, we have a full connectivity of our multimodal sensing that are connected to both of them. All of this is supported by our zonal ECU architecture and power and network architecture, which, all of this together provide a end-to-end functionally safe platform.
Okay, there's a lot there. This is really interesting. Let's dive in more here. So tell me more about TSMC N5A. Is that what it was? Talk to me about what does it mean to be automotive rated and ASIL rated?
Yeah, so the TSMC N5A is, let's step back a bit. So TSMC N5A is our kind of a leading de facto automotive node. And that RAP1 is, manufactured in it, and that gives us the best performance, power, and area. Foundries such as TSMC take leading edge nodes, and they work with hyperscalers and other companies to run just a lot of designs through it, and hundreds of thousands of wafers. And from this, they can get data of how reliable the process is, and then look at things like electrical failure rates and physical failure rates to fine-tune the process in terms of either design rules or manufacturing recipes to make sure that the devices are robust and reliable. So I know this takes time, and what this means is that we are not always on a bleeding edge node, right now it could be N2, but we, as a system company, we benefit from working on a mature platform so that we can put it into our safety critical systems.
Sure, that makes sense. So TSMC, they come out with a new node, they kind of run it through hyperscalers, through mobile, and eventually they have all this data and a lot of confidence about that process node. And then they start to build, they make an automotive node, which they feel, confident in reliability and yield, which is important because these are going into automotives that are going to drive us around without us paying attention. So it's kind of part of the safety case, essentially, is this.
Correct. Yeah.
Yeah. And then, okay. And then you also talked about determinism and redundancy. So I think redundancy is obviously pretty clear. Like if something happens with one chip, having a second chip to fall back to makes a lot of sense. That way, when I'm texting and not paying attention, I don't even know that the chip that, there was a problem. Say a little bit more about the determinism. Is that really about sort of like a latency budget and just knowing that things are going to happen in a certain amount of time? Or is it also about knowing just there's always the same outputs given the same inputs?
It's about, determinism is, both those things in a sense. We have our LDM that is trained on training set, and then we have those weights that we run on the RAP1. So that's one piece, and that goes through extensive testing, and from that autonomy team does that. That from a hardware point of view, all the full LDM is mapped to the hardware resources, and from hardware point of view, we have to make sure that I said earlier, this perception task runs in a certain loop, that these tasks that make up the large driving model can be mapped to all the hardware resources. We have, certain ISP resources, we have certain DMA resources, we have certain memory bandwidth, we have, obviously our neural network engine. So we have to make sure they are all mapped to these resources so they're efficiently utilized. And all these different sensor streams coming in can be processed through them so that we can provide deterministic latency up through the automotive stack.
Awesome. All right, so let's dig into the chip. I think this has been really interesting talking at a high level about the workload and some of these constraints that people don't think about all the time. But let's get into the RAP1 itself. So earlier you mentioned an NPU, you mentioned, ISP, you mentioned, we've talked about memory, and you talked about, like application processors. Maybe give us again, work through it again at a high level and help us understand. I'm really also curious into, what you guys felt like was important for you to design. And, I know, for example, you used ARM for CPU core. And so talk to me about like what you guys wanted to own yourselves and where it made sense to like partner with someone for their IP.
Yeah, that's a great question. So I think it's a two-part question. So I'll answer them in that order. The first part is just what is in the RAP1 chip, right? Just at a high level, what are the blocks? Yeah. So, in the RAP1 chip, we have several different subsystems. I'll walk through them. First one is our always-on processor and secure boot. So that is used to do secure boot of the chip, and as well the always-on processor when we're in low power mode can do such certain housekeeping functions. The second one is our Rivian safety island, which has ASIL D rated R52 cores. And the third one is our interfaces. The interfaces essentially are used, high-speed interfaces. We use to interface to cameras through standard interfaces like C5. We also have interfaces to interface to the radar and LiDAR, GPS, IMU, etc. So all that kind of brings the data in. And all this needs to be processed. So we have a sensor pipeline. And so we talked about the ISP already, and we have some pixel processing to pixel DMA to process the incoming camera streams. And then after that, we have our, all this feeds into our neural network, in-house neural network engine that I just mentioned already is also designed with ASIL ratings in mind. Then we have our general purpose compute, which has 14 ARM A720 AE cores, as well as a general purpose GPU. Now, all this together, they need to talk to each other. So we have a high performance NOC that can connect all these, and they connect to the memory subsystem to be able to transfer data in and out of the memory. So that's basically RAPs. Now, you talked about like, what did we, decide to do on our own, and what did we decide to, outsource from other companies? So, as you know, it's quite common for chip design to be able to get interfaces and processors and integrate that into the chip. So we need to focus on where we can add value and differentiation. And then we went through a disciplined approach, looked at all the IPs available outside. You have even like neural network accelerators, etc. And we determined that where we can add the most difference is because we have a full understanding of the hardware-software stack and we're vertically integrated. We can add the most differentiation by designing our own neural network engine. Then we also looked at the system and we said, hey, maybe it makes sense for us to design our own low latency chip-to-chip interconnect, which we call RivLink, and we decided to build that as well. So for the other IPs, like you mentioned, like for PHYs, for CPUs and stuff, we looked at the landscape of what's available in which technology, did a due diligence and bake off, and chose the right IP.
Gotcha. Yeah, that makes sense. You guys, at the end of the day, you're putting a system together, and so you're asking like, which Lego blocks can we use from other people, and where does it make sense for us to actually build the Lego block? And it sounds like, obviously, given that you're kind of doing hardware software co-design with the LDM team, made a lot of sense to make the NPU yourself. And say more about RivLink, the high-speed interconnect.
Yeah. So as you know, designing a chip is a multi-year effort, and you want to make sure that whatever you build today has legs. And you also have to look at the constraints, right? How do you balance the constraints? And what we looked at was, hey, we have this design that we need to do, and we have a certain application in mind, which is our autonomy application. And then we also looked at, okay, we've been around the block enough to know that we don't want to build a kind of a single purpose chip, and we want to make sure it's extensible to other systems. So then you look at what is the right building block chip you can build, and then you put in interfaces like RivLink, which is a low latency chip-to-chip interconnect that allows you to gang multiple of these chips together depending on the system requirements.
I love this. Okay, this is really interesting. So you're saying that when you guys thought about designing this chip, you're not making an ASIC that's really just like built super specifically for autonomy. You're actually trying to abstract a little bit and think. You mentioned physical AI earlier, and think about like, hey, what are the type of workloads that would have a perception stack, maybe multimodal, high bandwidth, and need to process that data, run inference on that data, and then have some sort of action come out of it. And of course, autonomous vehicle is one, but it sounds like you're also thinking a little bit bigger picture than that, because an autonomous vehicle is just like a big robot. It is like embodied physical AI. And it sounds like you're designing the chip so that if you wanted to, you could maybe chain multiple chips together and support other similar workloads. And so, affirm if I'm understanding that correct. And then also, this is probably a good segue, like tell us quick about Mind Robotics and how that fits in here.
Yeah, I don't know a whole lot about that,
Sure.
to be quite honest. Right now we are focused on getting RAP1 into production and get that into our Rivian R2 vehicles. So it's up to Rivian leadership to figure out like what other applications this chip might have. But as someone who's worked on chips for a long time, so we always have to make sure that we build chips that have multiple purposes.
Totally makes sense. So you're leaving the door open. You're thinking at design time how to leave the door open for other use cases.
Right. Correct.
Yep, that makes a lot of sense. Okay, so tell me, like, if I recall, it's like 800 tops for the NPU. How do you come up with how much is enough tops? Like, obviously, you need some headroom probably to grow into, but like, how do you, at a high level, like decide? Yep, 800's good.
Yeah, that's a great question. Performance is something that we think a lot about. And, the first thing that you have to do is, look at where this is going to go. This is going into a vehicle, and the vehicle is going to have a lifetime of several years. So you have to be able to put in the compute now so that you can allow for over-the-air updates so that software team can continue to add features and functionality, right? That's the first thing that you have to think about. Then you also have to look at your foundation, which is like, hey, what constraints do you have to work with? Starting with our TSMC N5A, and which we already talked about is the right sweet spot for us from a manufacturing point of view. But then when you look at the TSMC N5A, then you say, hey, what does the yield curve look like for this? What's the die size, that gives us the best sweet spot in the yield curve? And for that die size, what is the aspect ratio that gives us the maximum MFU or mask field utilization? These are some of the foundational drivers of silicon economics. Then once you have that dialed in, then you have to look at the interfaces that take up area that you must absolutely have, like DDR interface or high-speed interfaces. You also need to allocate enough what you call beachfront for power delivery that takes up some room. Then you also have your sensor pipeline where you need all these things like ISP, DMAs, et cetera, that take up room. And finally, you're left with some area where you can put in compute, right? And there you also have to split between general purpose compute and neural network compute. So then what we did is, okay, we look at our applications and profile them that are running on a previous generation system, and we say let's pick a target of, let's say, 3x the performance, and see how we can fit into that. So generally, that's where we did, but we said, okay, let's give a little bit more headroom and target 4x the performance. So that's how we arrived at it.
Cool, that's awesome. I like it. So I guess for listeners at a high level, it sounds like at the start, you're thinking about essentially like, how big is this die going to be? The bigger it is, the fewer there are per wafer, so the more expensive it is. And the bigger it is, the worse yield because you just have more surface area to have a defect. And so you're kind of thinking about a sweet spot for the die size. And then you're basically starting with all those other blocks that are non-negotiables. You've got your IO interface, memory interface, all that stuff. And then you're kind of left with some room for compute, for CPU cores and for the NPU. And then you kind of just played around with, hey, what if we have this big of an NPU and this many CPU cores and profile your workloads and ask, like, can we unlock 3x, 4x and get to a sweet spot, call it good?
Yeah, exactly. I mean, you have to work within constraints and, try to the best job you can so that you can, give the end of the day, if you have to deliver value to the customer in a vehicle platform that, they need to be delighted with all the over-the-air updates that they get. And, we have to keep all those constraints in mind.
Yeah, makes sense. Doesn't sound easy, but that sounds fun. Okay, so let's get into the why behind custom silicon. Now that people understand, hey, there's a big perception stack, there's all this data flowing in, there's all these real-time constraints, you have to have a lot of compute to do the inference, you have to have headroom so that you can do over-the-air updates and think about this, hey, this car might be running 7-8 years from now, so there's a lot to think about. You've done all that, and it's definitely possible, and you've shown, you can get 4x performance. But the question in everyone's mind is like, why can't you just get that off the shelf from like merchant silicon? Why does it make sense to design your own silicon to unlock this level of performance?
Yeah, so I think that's a fantastic question. And so I'll try to answer that in two parts. The part one will be like, some about like how vertical integration affords us some unique opportunities. And part two also about what can we do by having this in-house in terms of maybe doing some shift left, right? So because we are vertically integrated, we understand our application really well, and we can build a chip that executes that really well. Whereas merchant silicon might have to guess at what the application might be, and because of that, because that they have to take a guess, they have to cater to multiple customers. And then that has some implications on what interfaces they use, how they architect those interfaces, which may have implications on system cost, right? I'll give you an example of that. And then our neural network engine also is, we closely work with our autonomy team, and is purpose-built for this application. And we can look at, what is the metrics like dollars per top, so that's something that's important as well. Now, I talked about, system design and why that might work well in a vertically integrated company like us, because we know, for example, what our memory configuration is. We can take the memory and put it into a multi-chip module, and we've done that for RAP1. And what that allows us to do is it takes the memory off the board and pulls it into the package, and then that means that now you don't have to use a high-density interconnect board, which can be more expensive. Mm-hmm. You can save that real estate and have a smaller board. So, whereas if you are a merchant silicon vendor, you cannot control what their system design choices are, how much memory they need, etc. So you can't do these kinds of optimizations, right? So that's one part of the answer. The second part is, because we are vertically integrated and we have a full knowledge of our hardware software stack, we can look at everything from system, sensors, thermal and power budgets, etc., as well as the application drivers, and try to find optimization points where they make sense. And you can just walk over to the engineer and have a chat with them on the whiteboard and say, hey, can we do this? Can we do that? And do either some microarchitectural improvements or fixes to make sure that we have a really efficient platform that we can provide. Now, this also allows us to do some like shift left, right? So a concrete example of this would be, let's say you're making the chip, you have fairly mature full chip RTL, then you can take that RTL, map it onto a prototyping platform, and start doing things like do your boot. You can do the driver development. You can do your middleware development. You can also work closely with your application stack to see what the bottlenecks are. And at this point, you can do things like, very easily look at, hey, I need to know more of the statistics. You can add some counters, performance counters. You can say, hey, there is some bottleneck here. I can add some microarchitectural enhancements to make sure there is no bottleneck. So, in summary, looking at the fact that we are vertically integrated affords us, opportunities from a system optimization point of view to save cost, and as well as make sure we can get the performance. And secondly, it also allows us to do a shift left, and it acts as like a force multiplier, so we can get the best available platform.
Yes, makes a lot of sense. So, it sounds like if you get off-the-shelf compute, it's not going to fit just perfectly to your workload, even though you're not talking about designing it to a very, very, very specific workload, but to your shape of workload, it's just not going to fit, because fair enough, a merchant silicon vendor has to think about many different workloads when they're building that chip. But then I like what you said also about, like, because you can do hardware, software, co-design together, you can shift left, because at the RTL stage you can make architectural tweaks, you can run software, test middleware, that kind of thing. Yeah, it makes a lot of sense. Yep. And then so it sounds like it unlocks by creating the custom silicon to the shape of your workload, it unlocks better performance, lower cost, because you can do stuff like take the memory and move it in and think about these kind of things, and then ultimately like get the chip out the door sooner, presumably, because you're not waiting for it and then dealing with it. You're shifting left. All right, so tell us a little bit more about like how it's getting done. I think people, of course, at first obviously Rivian's made the zonal architecture, so not that Rivian is just a car design company. You've had electronics as like a core competency for forever. But custom silicon again was a little bit of a surprise. And so like how big of a team are we talking here, and how long have you guys been working on this?
Yeah, that's a great question. So we, when we built the team, we wanted to build well, first of all, this is a bold endeavor. So
Yeah,
we have
totally.
to build we wanted to build a lean team that has all that's world class and it's multidisciplinary and that has understanding of all the aspects of doing silicon, right? So they have to have experience in, within the team, we have to have experience in SoC architecture, we have to have expertise in design, in verification, in packaging, signal integrity, power integrity, and physical design, and design for tests like DFT architecture. So we have to be able to understand every part of the process and put together a team that can execute on this. Now, it asked about how long did it take. So, given the complexity of the chip and that we had to build the team even as we were defining the chip, we were able to execute this in a relatively short amount of time. And so, we had to build a team, build a business case, and then say, let's a project start that had to go in tandem. So kind of that phase is a little bit diffused. So, but if you look at that, from that time to when we got the silicon in hand, when we like project go to silicon hand was about 2.5 years.
Nice. Nice. Yeah. You make an interesting point. You have to build the competency, build the team up at the same time you're trying to build the chip. So obviously that's going to impact timelines. Okay. Awesome. So let's see. At Autonomy Day, we heard we were going to get this like late 2026. I think on the last earnings call, it said early 27. But how are you going to celebrate when RAP1 makes it out there? It drives off the production line. What are you
I
planning?
don't know. I hope to be just waiting there, witnessing that. That'd be really cool.
Oh yeah.
It's been a multi-year journey, and we have a fantastic team, and we did great collaboration with our partners in the autonomy team, and work together to get to this point. And of course, we have to get this into production and get all the integration done. So all that is still work in progress, and we're working very hard to hit all our milestones. Yeah, I'm just hoping that I can witness that and do a big whoop.
There you go. I love it. Totally. I think I actually saw at Autonomy Day, maybe there were some custom t-shirts or something that people had. I hope you guys, are celebrating and making some swag or something.
We had those, the black one with the cartoon of the chip. Yeah.
Yes, exactly. Awesome. Well, hey, Mukund, thanks for the time. I learned so much. Stay in touch, come back. You guys put a 1 at the end of the Rivian autonomy processor, which implies that there will be a 2 eventually, and maybe someday a 3. So let's stay in touch. And if there's more, would love to hear more about it someday.
Thanks, Austin. It's been a great conversation. Thanks for the opportunity to talk about the Rivian autonomy processor. I think, we can claim now that we have silicon that we're truly vertically integrated company that capable of doing more than the space and delivering value to the customer through our products, and also advancing Rivian's mission. And taking RAP1 into production will also put Rivian squarely in the AI space, and we're looking forward to that.
Yeah, awesome. It's going to be a big next couple of years. I'm excited for you guys, and custom silicon is going to be a key part of it.
Right. We hope so. Thank you so much.
Awesome. Thank you.